Okay, some time a ways back, when we were talking about colliders, I encountered the wheel collider, and I said I'll come back and talk about the wheel collider uh, in the context of making a car. So the wheel collider is very different from the others, and it's designed specifically for vehicle wheels. It can do a couple of things. It can calculate the friction forward and sideways. This is what gives us our traction for accelerating and our ability to slide sideways, more or less. It also has a suspension that models the up and down movement of the wheel. Uh, um, some of this is accessible from the inspector, but a lot of it requires scripting to access. In particular, we can specify the motor and brake torques, the steering angle. We can find out whether the tire is touching the ground or not. And we also get a measure of how many revolutions per minute the tire is spinning. What it can't do is spin the wheel, the visible wheel uh, that replaces our that goes along with our wheel collider. Um, in general, the animation of the visible wheel, the visualization of it, must be done in scripting. So wheel properties. Uh, we have a center of the wheel. We have a radius uh, uh, done through its scale. Generally, we want this to be bigger than the visible wheel, which itself may have a normal collider. If the wheel collider is not bigger than the visible wheel, the wheel collider won't touch the ground. Uh, so and you do need a collider on the visible wheel if you want it to push objects around, something the wheel collider can't do. The wheel collider only touches the ground. Um, Settings include the suspension distance, and all of this is shown by a gizmo in our scene that's pointed towards the ground. Here I have an example over here of a cylinder which has as a child a wheel collider. And you can see the gizmo here that represents the wheel. The little vertical line here is its suspension, and this little dot down here is where the forces are applied. Wheels have a mass. Here's the radius that I can change and make the wheel bigger or smaller. Uh, uh, the spring has a damping rate as well as a suspension, a spring strength and damper, and it has a distance. So I can make the suspension longer or shorter. The force that's generated by the wheel where it touches the ground, both the sideways force and the forward backwards force, is applied at this little spot here. And we can move that around, which helps us adjust the handling of our car. If we make this higher, the force, the car doesn't tend to tip as much. But I'll leave it at 0 just to show this. And here, I'll let this run, and you can see the way the wheel bounces there. We have a spring. I have no damping, so it'll keep bouncing for a long time. And this is my wheel. Over here, I have this little unicycle, uh, which is also just in this case, a box with a wheel child, and I have a visible wheel that is the child of the wheel collider, this checkerboard thing. And I have a little simple script on this that lets me apply motor torque. So I can apply motor torque and the wheel spins. And I can also steer it. I can turn it to the left or the right. See it over here, the wheel turning to the left or the right. And that's all done through scripting. We have our suspension, we have our ability to apply force, and this is modeled by the forward and sideways friction in the torque versus slip curve. And this curve is defined by uh, uh, 2 points, the extremum slip and value and the asymptote slip and value. And we can look at this as a curve. The extremum slip and value, the value is 1 and the slip is at 1/4, and the asymptote slip is at 0.5 with a value of 0.5. The force that is generated depends on how much the wheel is slipping relative to what it's in contact with. As the slip increases, the force that it generates increases until we reach this extremum value. For slip beyond that value, the amount of applied force declines and it goes down to this asymptote value, beyond which it stays flat. And so we can define this asymptote slip curve with these 2 points, extremum slip and extremum value, and asymptote slip and asymptote value. And we see these here in the inspector, the forward friction slip and value, asymptote slip and value, and stiffness is just a setting that kind of scales this whole thing, and it's an easy way to adjust to make more friction. So that's the forward friction that is what's going to give our wheel traction to accelerate forward or backward. And then there's the sidewards friction, same kind of thing, except this is what the sidewards friction of the wheel that allows us to turn and maintain a straight path. We determine how much the tire is slipping based on the speed difference between the tire, the wheel, rubber, and its road. And this slip value is used to determine the amount of force exerted on that contact point, the little point here where we're accelerating. And we approximate this as a two-piece spline defined by the four specific values that make up our curve. So let's make a car here with this. Don't save. So here's a little car that I've made, and I'll go through the procedure of building this. This is all based on a tutorial that's available on the Unity site that also includes the scripts that I'm about to describe. So we start off with an empty game object that we'll call the root. This root just has a transform and a rigid body. In general, the rigid body default 1 kilogram is too light for the default spring settings. So a typical value for a car is about 1,500 kilograms. The car body is a child of this that we put underneath the as a child. This is just the visible car. This is what we want the car to see with the car. And so it's just the mesh filter and the mesh renderer and a collider if you want to have one. So we reset all this stuff and then we go through and define the wheels. Here are the wheel colliders. I have 4 of them: a left front, left right, left front, left rear, rear front, rear right, and I've defined each of these to have a radius. And, uh, and in this instance, I've also defined visible wheels that are flattened cylinders uh, uh, that look like wheels. So let's watch this thing go down its hill. Here's a trick. If I select the car, do a Shift F, and now play this, my scene view will follow that object as well. So you can see the wheels rotating here, the suspension going in and out as the thing rolls down the hill. Now, I haven't put a motor on this car. I haven't put a controller on that. That's something that we need to do in another scene. So let me go to this other scene here where I have a similar car set up. And um, it's basically the same. I have the car root with a rigid body. Of course, I have a car controller here. And I have the cube that's the visible object. And I have these wheels that are placed around the periphery of my little game object. And they have suspensions and they have application points and so forth. Um, so, um, so I've got my car all set up. And this just walks you through how to kind of set it up in an easy way. And now we'll look at our simple car controller number one. I'm going to provide some information as a pair of axles, as a set of axles. Each axle will have some information about the wheels that go with that axle. There's the front axle and the rear axle, but as you'll see later, we can make more of these. I have public floats for the maximum motor torque and the maximum steering angle. These I'll use to set the power of my motor and how steeply it can steer. In the fixed update function, I'm going to use the vertical axis to get the motor torque, and I'm going to use the horizontal axis to get the steering angle. Both of these that go from plus or minus 1, scaled by motor torque, or steering angle to get the motor and steering. And then I'm going to go through each of the axle infos that I have in my object. And I'll, if the axle is a steering axle, I will set its steer angle. If the axle is a motor angle, I will apply torque. Now, one thing I want to show you here is the axle information class. This is a system serializable class. This allows us to put it in the inspector and be able to see it. And it has a number of things. It has a left wheel and a right wheel, and it has a motor and a steering. Here in my car root, I have axle information. I have two axles. Each one has a left wheel and a right wheel, and whether it's a motor or steering. Here's the element one is the front left and front right, and it's just a steering. So I'm driving this. This is a rear drive car and a front steering. And here's my motor torque and my steering angle. So this is all ready to go. And so I can press play here and I can watch my car. If I press the up arrow, the car moves forward, the down arrow, it moves backwards. You can see the wheel colliders rotating here, and I can steer it by turning left and right, and my car accelerates and drives around the world. A little speedometer here to see how fast we're going. So that's all great, but it's not terribly interesting. here's that serializable attribute that lets you embed a class with subproperties in the inspector, the axle infos, of which there are two, of left and right, motor and steering, left and right, motor and steering, and torque and steering angle. So we want to have visual wheels attached to our car. And there are a number of ways to do this, but there are also some gotchas that we've got to do with. And as I mentioned before, the way we include visual wheels is through scripting. We're going to orient and position our visual wheels so that they match our wheel collider. So I'm going to add a function, apply local position to visuals, that takes a wheel collider as argument. It tests to see if I have any children. What I'm going to do is let me get to the next scene here. My test car with cylinders. So what I've done, I've got my wheel colliders, and they each have a child that is a cylinder. I have the wheel collider, and I have the cylinder wheel that is its child. So I'm going through and looking for children. If the count is 0, that means there's no wheel and I return. Otherwise, I get the transform, I get the collider off that child, and I have a position and rotation that I'm going to get back from the collider's get world pose. So the collider is the wheel collider. That's this thing that we passed in as an argument. And I'm going to get its pose. And putting an out here means that these are output. So I get the position and rotation of my wheel. And I then assign that to the visual wheel's transform position and rotation. So I need to add something to my fixed update function. And I'm doing this in fixed update because this is all physics. I don't want this in the update function because it fires at frame rate, whereas the fixed update fires at regular intervals. So I'm going through each of my different axles, setting steering and motor, and applying local position to the left wheel and the right wheel of that axle. So I'm applying that to each of these two wheels. Now, one of the gotchas is that if we use a flattened cylinder, which is what I did kind of naively over here, the cylinder axis is oriented along the y-axis, and the wheel collider orientation has the y-axis up. So if I look at the local axes of these things here, my y-axis of the collider is up, but my y-axis of the cylinder is out. So this is going to cause a problem here in just a minute. And it's kind of an interesting problem. I'll show it to you anyway. And here it is. This is car route broken wheels. So when I start off immediately, what you see here is that the wheels have assumed the orientation of the wheel collider, which is wrong. The y-axis of my cylinder is up, and that makes these little flappy things that don't exactly look like wheels. They do look kind of cool, but they don't look like wheels. And so this is not the way I want to do cars. There are a couple of fixes for this. You can use instead of using a flattened cylinder, you can use a flattened sphere that you would flatten in the appropriate direction, in the X direction. Or you can make an empty object with a flattened cylinder as its child, rotate it within the parent so that its rotation axis is correctly aligned. And then you get something that looks like this, um, test car with cylinders fixed, which I've got my wheels, and the wheel collider uh, has a child, the wheel, which is just a transform oriented appropriately. And inside that is the flattened cylinder, now turned 90 degrees in the z-axis, so that it's oriented in the correct way. And now our car has properly oriented wheels. We can steer and we can drive forward and go over this little ramp and drive around. And we've got our car. Very cool. So here we are. Here's a version of this car operating on terrain. And we can see that we can drive it around terrain, and it, whoops, it, well, there I ended up off that. Can't get up. Oh, made it up. Okay, so all very cool. I'm going to stop sharing. I'll come back and show you some examples in a subsequent video. Stop sharing, and I'll stop recording and end the video. Bye.